Um, okay, thank you for coming to my talk called 7 Vulns in 7 Days, Breaking Bloatware Faster Than It's Built. I'm going to take you through a bit of a journey of what was about a week of discovery of learning how broken bloatware is. The story starts during my summer holiday where I'm playing games. I really enjoy playing games, so I spend a lot of time doing this. But after one of these long sessions, I sort of close whatever I was doing, and I have a little pop-up on the side. And at this point, I see Asus DriverHub, appropriate for my computer, is asking me to click here for one driver update. I click this update, and a browser opens up to driverhub.asus.com. Not really too sure yet what this is about, but it's fine. I sort of go through and click the relevant driver, let it update. And eventually, I'm just presented with this modal, a browser modal asking me to restart my computer now. Now, I've been thinking a lot of things at this point, but when I got here, I was really wondering what was cooking. Is this a cloud service? Is this an interaction that's asynchronous in some way? Like, really, what is cooking here? Anyways, I get back to the modal, I hit restart, and instantly, my computer starts rebooting. Like, really fast. I have a good internet connection at home, but this is suspiciously fast. The computer comes back up, and I'm immediately back at the driverhub.asus.com site, opening the inspector, and I realize that it's interacting with a web server that's running on my computer. I didn't realize this web server existed up until this point. That was the end of my summer holiday gaming experience, and I now started digressing over to some more reversing. So in this talk, I want to tell you a little bit more about that. Before we get there, a very quick bit about me. My name is Leon Jacobs. I'm from South Africa, and I work in Orange Cyber Defense's SensePost team. I really enjoy researching, hacking, building stuff, and you'll probably find a lot of my open source contributions on GitHub. Today, I want to tell you this story about a bunch of bloatware that I took a look at and the vulnerabilities that existed in there. We're going to be looking at Asus DriverHub, MSI Center, Acer Control Center, and Razer's latest Synapse 4. All of these products have been fixed, so if you insist on still running this stuff after this talk, at least update to the latest version. You're going to see usage of a whole bunch of tools. Most of them will probably be familiar to you, and we're going to look at a whole bunch of code. I've taken quite a bit of effort to try and focus on the bits of code when we need to look at that, what you need to look at, and what it would mean. But if you want to look at the slides later, you absolutely can. With that said, let's focus in on Asus DriverHub for a moment and the 2 CVEs that I found there. One of my favorite tools to get a sense of what sort of processes is running on my computer is Process Explorer. Opening Process Explorer and sort of seeing what's related to Asus DriverHub, I see 2 processes that look like this in this tree. The adu.exe had a TCP port that it exposed. This has allowed some TCP connection to happen. Now, at this point, I wanted to play around a little bit, but I realized if I'm going to do some vulnerability research, I probably want to move this stuff into a virtual machine. A snapshot, the ability to revert, etc., is really handy for long-term research. However, if you try and install DriverHub on a VM, it appropriately tells you this is not an Asus product. In fact, it's a Parallels VM, which is fine. Thankfully, this is not a hard check to get past. You could open that installer executable in something like Binary Ninja, find the check that says, is this an Acer's product, and patch it out. Once it's patched out, save the new executable, and the installation should complete. Fairly easy. With it installed in my virtual machine, though, I get to a point where it now has the browser telling me, again, and appropriately, that this is not an Asus product. Fine, I can take that. But I'm also at a place now where there's interaction between the browser and what I now know is that local web server. So, using our favorite tool, Burp, I'll inspect the interactions between that client, the browser, and the local server. And there's one flag that the local web server tells me on an initialization routine that this is not supported. Thankfully, I can flip that false to true, and suddenly my product is supported. It gets you to a screen like this where, sure, I don't have any appropriate drivers, but I can install this Armory Crate installer. I'm now at a place where I was initially, but in a virtual machine, allowing me to instrument and inspect this environment a lot easier. So back to those 2 processes, the one we're going to focus on today specifically is adu.exe, because it's listening on this TCP port 5300. If you were to open that in Binary Ninja and sort of follow string references to get a sense of what's happening, you'll eventually end up in a section which looks like HTTP endpoints that you may have seen already while interacting with it. following where this reboot reference exists, at some stage you'll end up on some code, which is a very simple implementation for running exit windows, the Win32 API that you would call if you wanted to reboot your computer. So to sort of put all of that in perspective, the way this Asus DriverHub really works is you browse to the public website, some JavaScript makes fetch requests to the local web server that ultimately makes some Win32 API calls in a C world. Now, if I wanted to play with this, I sort of wanted to get to a place where I could replicate this request and fiddle with it. One way to do that would just be to wire up some PowerShell one-liners so that I can continue experimenting with how this works. Over here, I'm just making a very simple post request to that reboot endpoint that's on my computer. Again, the intention here is for me to get a sense of how does this work. When I make this request, I get an access denied response. A little bit strange, but that's fine. It's already something to look at. What's really nice about a lot of these products is they have a lot of logging. They'll tell you what's wrong. One of my options here is I can go and look at what the code flow is server side, or I can just read logs. In this case, you'll find that that adu.exe emits quite a lot of useful logging, and it sort of gives me a hint on the first issue over here, where there's a context around an origin telling me that there is the access denied error emits from there. Now, I made some inferences here. If there is an origin, we've seen an origin header before. So in my PowerShell one-liner, I just add the origin, make the request, and a new error comes up. Now, if any of you have done this kind of work before, you know a new error means progress. So I've made some significant progress at this point. However, still back at my logs, I can now see, great, I've passed the origin check, but there is this misspelled word entry followed by a line saying, the request body is empty. That's a really useful hint that, okay, it's a post request. Often we need to have some body attached to that. I have two options at this point. I can continue in Binary Ninja and figure out what that request might look like, or knowing that these requests are emitted from a web server, I can look at the JavaScript source code where that might come from. Again, as you probably would expect, it's a minified mess, and it takes a little longer than I initially anticipated. But at some stage, you'll come across a block that looks like this, that really says there's a post body that's stringifying two keys, the event and the command key. Change that over to my PowerShell one-liner, where I have the command to reboot as an event, and I've now replicated the reboot that I have on my browser. Okay, so with that out of the way, I want to talk about the first bug in this context. And it's something I'm just going to call the string contains bug. I don't really have a fancy name for this. To understand this bug, we need to have a quick segue in knowing how origin header checking usually works. Imagine a browser with two tabs with exactly the same content served from a different domain. It's exactly the same replica of each other. If we were to replicate the reboot feature, in whichever tab you're busy with, that fetch request would make that post such that the reboot is asked for. As a security feature for the browser, though, it would add an origin header. A developer cannot control this header, and this is a way for who receives the request to sort of try and identify who made this call. The way this is implemented in adu.exe goes, if this is from asus.com, the request is accepted, but if it's not from asus.com, the request would fail. And it's sort of a way to prevent anyone from connecting to the web server, which sounds like a great idea. Usually while I'm reversing these kinds of things and I find code that's called quite often, and I don't have exactly the right idea on what it's doing, I'd rename the reference with a bit of a question mark. So in this case, at some stage in the past, I found a function that looked like it was doing a string contains, I think, and then specifically this call to, or invocation to that function jumped out at me. This code was part of the origin header checking, and it is a string contains is the name I gave for it. If you go into the function to sort of see how this looks, it's really just a mem compare over an iterator, checking each byte over time. To visualize what this might look like, imagine you want to check if driverhub.asus.com matches the asus.com origin. The iterator will pass along until it's finished with the string, and it will return OK, exactly as you would expect it to do. But what if you gave it driverhub.asus.com.local? The iterator will continue, and when it reaches .asus.com, it's happy, ignoring the .local part at the end. This means I can invoke that reboot request from a non-asus.com origin, which is great. Another way to reboot a computer. With what we have so far, you could use this and send it to your friend, say, cool, click here, and your computer reboots, and they're off Discord or whatever you're doing. But more importantly, we have an ability to have arbitrary origins interact with this DriverHub web server, not the way it's intended to be. Now, rebooting computers is a lot of fun, but it's not really the sweet spot. What we really want is to get code execution. The DriverHub, the adu.exe program, has many HTTP endpoints. One of the more interesting ones is the update app one, and I think you can already see where this is going. Looking at the JavaScript side, we can get a sense of what that request looks like, and if we focus in on the payload, we can see URL as one of the keys of something that you might want to populate. In my case, I go for pwn.local, add a random executable, update my PowerShell payload so that it can see, so it mimics what that request might be, and it obviously fails. But I have this amazing logging that tells me what's wrong. You see, the URL doesn't have this .asus.com part in it. Thankfully, we already know about the string contains bug, so we just changed our URL to now have a .local endpoint, which is a domain I obviously control, and we're back to our log to see how far we got. It's not successful yet, but there's a new error. And in this case, there's a signature validation related line that we get. So we've gotten to a point where anyone can invoke this endpoint, but you can't run any sort of executable, which wasn't great. So the next part I decided to focus on is how exactly does this signature validation work? Well, you see, it looks like if you have a PE executable that just contains a property with the name Asus Tech Computer Inc., your binary is signed. The reality is, thankfully, previous researchers have tools that will let you copy a signature from a legitimate binary to some arbitrary other one, mimicking properties, specifically realizing that this is not a validly signed thing. It just looks like it is. So, stringing all of those things together, I want to show you a demo of what a one-click RCE in Asus DriverHub in a vulnerable version would look like. In the demo over here, on the left-hand side, imagine this is a victim's browser. They arrive in your URL in whichever way it might be. You're browsing a weird website and you get redirected. Your friend sends you a link on Discord. Imagine whatever is possible over here. On the right-hand side is really I'm just going to tail the logs for the DriverHub web server so you can sort of get a sense of what the execution looks like. So first things first, we start tailing the logs. On the left-hand side, I browse to my POC. It takes a second to interact, and we get code execution with one click. Now, thanks. Of all of these components in DriverHub, though, everything runs as a normal user. You're not getting elevated code execution at this point. But knowing the kinds of computers where the software runs, you're usually an administrator with a UAC level in the default, at least showing you that some elevated action is being requested. Well, it turns out if you, in some cases on Windows, there are some heuristics where Windows tries to automatically determine, is this an installer, it might need elevation, etc. You can make that more predictable by signing a side-by-side manifest, or a UAC manifest is what some folks call it. That manifest looks something like this, which really just says if you run this, please try and run this in a higher integrity level. If you have Visual Studio installed, you can run empty.exe, pass it the path to where the manifest is, and tell it which executable the manifest should be applied to, and which resource position. Visually, you may have seen this kind of stuff before with the little yellow and blue shield that when you double-click it, you sort of expect that little pop-up, and in a corporate environment, you might need to put in credentials or just press OK if you're an admin already. In the case of Asus DriverHub, though, in the way adu.exe works, that UAC prompt does not appear. So if you were to apply this manifest to a POC, and it's run with a user that is an administrator with UAC on its default, it's effectively a bit of a UAC bypass. So in this case, the POC adds a local user to the local administrators group. Talking about how pervasive this is, though, I did wonder how did this stuff end up on my computer in the first place? It turns out my BIOS has a setting to automatically install this Asus DriverHub when Windows is installed. So this gives you a bit of an idea of like someone might be running this stuff without realizing that they have it, which isn't great. So in summary for Asus DriverHub, it's either an alternative to reboot your friend's computer or a way to execute code, and depending on the privilege, it could be a higher context. It can auto-install itself if you have this setting on in your BIOS, which is on by default. But effectively, it's really just a misuse of this really strange RPC mechanism. Using HTTP from a browser might seem convenient for users, but as you can see, it can be quite detrimental from a security perspective. Something I'm really excited about, though, is there's a draft Chrome spec which tries to gate access to local network endpoints. It'll be much like how if your webcam or your microphone gets accessed, there'll be a little bit of a pop-up saying this website is trying to access a local resource, which I think is a really nice way to sort of avoid this unintended execution later. Finally, the disclosure was a little messy, but I'm going to talk about that a little bit later. So this is still in my holiday. I'm sort of 1 or 2 days in, and I'm a little excited. I found a cool bug. Admittedly, I'm shaking a little, like, what does this mean? What can I do? Etc. But it wasn't long until I realized, what are other vendors doing? I'm a little upset, and I think, if this is how it starts, how's the end of this journey going to look? I decide to Google around. Asus DriverHub alternatives. What are other vendors, other products? And by random, really, this is where the targets are. I had a long list of targets I could obviously go through, but I decided I'm just going to go for whichever one gives me the highest chance of vulnerability quickly. Unfortunately, the next one was MSI Center, and there were 2 CVEs in this case. The interesting thing about MSI Center is when you install it, they ask you, when you run the software as a local user, please add your local user to the local admins group. This is the way the software is supposed to work. Which is interesting because if you look at all of the processes that back the software, everything's already running as admin. I don't understand why me as a user also has to have the GUI as an administrator as well. But anyways, like before, if we look at one of these processes, you'll see MSI Central servers listening on 2 TCP ports. And already, from what I've seen before, I sort of got a sense of where this might be going. Now, when you open the GUI client and the way it interacts with the web servers, some of the communication, based on the fact that this is TCP, we can intercept that with Wireshark. And looking at it in Wireshark, you'll see something that looks like this: an arbitrary byte stream that I'm not too sure what this means yet going in, and a response that looks like JSON, like that's something I can interpret. So while it's not HTTP, it's already an interesting thing to take a closer look at. The client for MSI Control Center is written in .NET, and really at this point it becomes a bit of a code review. I'm not doing any weird debugging or strange symbol renames. It's quite easy to sort of follow along on how things work. We're not going to go through all of that reversing, but I'm going to highlight 4 key points on what you'll learn here. MSI Center starts with a launch server invocation. It does some housekeeping and essentially opens a TCP socket to accept new connections. It registers 2 callbacks that run some code when a new connection comes in and does some dispatching when some data is sent. When data is sent, though, whatever you are sending gets serialized into a normalized structure and then sent along with the data response function. Inside of MSI Center, they have this idea of commands, and they're defined by these sort of byte arrays. Here's an example of a reboot and uninstall command, but you sort of see when you read more of msicenters.net, there are many other commands that are implemented as well. Based on these commands, the way they sort of figure out what should I be doing is having this sort of dispatcher thing that they have going. You see, when some bytes are sent in on the socket, if it matches a command, there's this really, really big, messy if-else statement that gives you an idea of where the code must go next. It makes it surprisingly hard to reverse when you're getting there. A fuller example of what the shutdown might look like is something like this, where we're comparing some bytes that came in. There's a little bit about a plugin loader, more on that in a second, but finally does this restart by just running the shutdown now command. So with what I've learned so far, I figured the exploit or the way to interact with this is very easy. I just need to reconstruct those bytes and send it off to that TCP socket. Nothing really hard. Except when I do exactly that, nothing happens. I haven't found logs yet, but I figured I needed to take a closer look at that protocol. You see, the first 4 bytes over here are bytes I haven't really found in the code. I'm not sure what this represents yet, but the bytes that follow that, those are familiar to me now. I've seen them match other of, like the reboot and uninstall command. So for my POC, I decided I'm just going to take the 4 bytes I've seen already. I'm just going to put it in the front and sort of hope. And that's exactly what I've done here. You won't believe it, when I send this along, my computer reboots again. And that's my POC for the initial way and how I can interact with that. Now, it's interesting that I can reboot, but more importantly, from a lower privilege context, I can interact with a process that's running in a higher privilege context. This is a very exciting primitive. Before we talk about some vulnerabilities, I want to take a quick segue into the software architecture of MSI Center, because I think it's quite interesting. There's clearly a large team working behind this, and they sort of have a way of working so that different teams can plug in different pieces of code. MSI Center has this idea of a component loader, where the program files directory, when it starts up, gets scanned for any DLL that matches this pattern, API_.dll. So if you want to write code, you want to write a component, you'll have a DLL that matches this pattern. Those DLLs, all of them, tries to be loaded and has a specific entry point that gets matched. And once they're registered, they have an ID that gets written to the registry. When you look at this a little bit closer, what it really means is each of those DLLs as a component have a unique ID, and each one of those components implement unique commands. So when we reverse that back to what we saw on the TCP stream, the first 4 bytes actually tells us which component / which DLL we need to target, then which command do we want to run in there. From a TCP socket perspective, once the data is sent in, this sort of dispatcher runs, which goes, what is the component ID, send the rest of the bytes off to that component, and hopefully it knows what to do with that. Cool. So now knowing how this stuff works, let's talk about the first vulnerability, which is an LPE in MSI Center. One of the commands that I found is this auto-update SDK. The component has that ID, and it lived within the main MSI Central Server module. The command itself accepts 2 arguments. One is a target, and one is some arguments. So you could probably see where this is going already. The way that works is, when you want to run this target, is whatever you want to run gets copied to C Windows temp. Once that file is copied over in a predictable name, it runs another function which does execute task, which actually schedules a Windows scheduled task to run immediately. Once that's done, so before the scheduled task happens, there's a quick code signing check that happens. Unlike the Aces example at this point, they're actually using the code signing check effectively. When verified trust actually checks that this is validly signed code. So without having MSI's code signing certificate, I won't be able to run an arbitrary executable. That kind of left me in a little bit of a kicking rock state. Like, I found this very juicy, obvious way in which I can interact with the privileged service, but I can't run code. Until I realized, let me take a look at this flow again. You see, if we zoom in on how AutoCommand Update SDK works, the first step it does is to copy this target, like I've said. So imagine we have prog.exe, it gets copies to MSI Center SDK.exe. The verification happens after that, which then runs the win-verified trust over that copied version that we have. Finally, the scheduled task gets created, and that means that that MSI Center SDK will get run as system fairly soon after we're finished here. The problem here is the binding between the verification and running the scheduled task does not exist, which presents us this opportunity for a race condition. If we very quickly invoke this function more than once, we can get to a case where how does the scheduled task know which target it's going to run? To visualize that, imagine I try run copy target very quickly. Once with a legitimate target, this MSI toast server, I don't know what it does nothing when I double click on it, so it was a handy target. What made it more attractive, it's validly signed by MSI. The other one could be my exploit, the pwn.exe. Once those targets are copied over and the verification occurs, like I said, how does the scheduled task know which one it's going to run? Of course, the verification will fail for pwn.exe, but there is a window of opportunity there where the executable actually exists. So my exploit plan here is to race execute and have 2 threads. One loops copying over the legitimate toast server, who knows what it does. The second one is then my exploit that tries to add a local user. And again, the scheduled task now doesn't know what to do. So we're going to look at a quick demo of doing exactly that. This is going to be, it'll just be some command line stuff. MSI Sensors GUI is running at the back, the vulnerable version. We'll start by checking the users on the system, then try and add an MSI user. This will obviously fail, which I'll then invoke the exploit, which is going to take a target argument of what do I want to run. Add user tries to add the user. When we win the race, we should now have a new user added as an administrator and have a local privilege escalation. Now, exploiting those race conditions is okay. It gets us what we want, but really, there is an even simpler way in doing this. You see, there's another command that calls run AMD VB flash setup that lives in this module called API support and uses execute task, but not the one with the code signing. It uses its own implementation. And I can imagine the teams here maybe migrated to a more common module or whatever the story here is. But the nice thing about this re-implementation, it does 0 validation whatsoever. It just takes a target path and runs it as system for you. That means my exploit becomes very simple, where I just now take that module prefix, the command I want to run, which is the one I just identified, give it a path, and I get privilege escalation even simpler. In the POCs that's released later, you can see this in action. Okay, so MSI Center summary. It's another way to reboot your computer, and maybe I should have renamed this talk to 7 ways to reboot a computer. Or it's a way for you to execute code in a privileged context and get LPE. This MSI Center stuff comes installed in a bunch of laptops that you would buy off the shelf. Many of you probably uninstall this bloatware that you get or just do a fresh install, but it gives you an idea of some of the coverage. But as a common theme, it's another misuse of a strange RPC mechanism that's probably not necessary here. Okay, so segue into what is my next target. We're sort of day 3, day 4 into this thing. I'm sort of having a bit of fun that these things are like whack-a-mole. It's not too hard to find these vulns. Who's the next one that I'm going to look at? And Acer Control Center is the next one. There are actually 2 bugs here that they decided to do one CVE. It's fine, but let's take a closer look at it. If you were to run this software, this is the first and only time I saw the GUI, but it would look something like this. But when you look a little bit closer at what the backend looks like, there is a privileged service called ACC SVC that runs a system, and it has a named pipe. So no TCP service in this case, just a Windows named pipe. Architecturally, there's almost like a client-server thing going on here. The server side is a native Windows C++ binary that runs a system. The client is a .NET binary, which I'm very excited about because that's a code review. It's not hard to reverse that. And the way these 2 components talk to each other is with this named pipe. Now, reversing the client a little bit more, one of the functions you'll come across is this function called send command by named pipe. It takes a handle on a Windows named pipe, a 7, which I don't know what it means yet, a target, and 113. 2 integers that don't mean anything yet, but sort of gives me a good idea of what this function does. In the context of the server setup here, when that command gets sent over the pipe, there is some code path here that finally runs this create process as user, taking that target argument as one of the arguments that it needs to run. So to implement this POC in terms of invoking this functionality, it's actually very simple. I take the .NET code that already exists, I start a new skeleton in Visual Studio, plonk that in, connect to the named pipe, and ask it to run Notepad as a random example. The thing that's really confusing to me here, though, is the target processes I'm running are not elevated. They seem to be running as the user I am running as now. Fine. I sort of park that for a moment and take a closer look at the name pipe. And a really nice thing about it is this pipe is configured to get file all access. So while that's not an LPE, it allows remote folks to interact with this name pipe. So at least RCE, and I'll take that. So we're going to take a quick look at what this looks like. The vulnerable version of Acer Control Center as an RCE. On the left-hand side, I have a VM as my attacker. On the right-hand side, I have a victim that's running this vulnerable version of Acer Control Center. The POC on the left is going to take a target IP and an executable that I want to run, that runs there already, and effectively is going to connect over that name pipe and run it. First, I just check my sanity by what IP is this VM. Then CD to the POC. I run it, connects over the pipe, and I have access on the other side. The crucial thing here is there's no shared authentication context between these 2. This is just my ability to connect to that Windows name pipe on the other end. Now, this is an interesting case, but the thing that really bothered me here is why would that ACC SVC run a system but execute code as a normal user? What does that 113 mean? And if we make the assumption that 7 might be a command integer, what other commands might exist? If you were to reverse this code a little bit more in binary ninja, you'll end up in this block here that sort of has a bunch of function definitions or pointers to functions in a section. Run command is obviously the one I've already been reversing, which is why it's renamed there. But when you see the actual caller invoking these functions, it's this offset-based thing, where if you pass 7, it's a base pointer plus 7. If you pass 6, the base pointer plus 6. So clearly there are other commands, but I wasn't sure what any of them were doing. Thankfully, I have a client implementation already that I can play with. So the only thing I really needed to do was potentially use some Frida to attach to each of those pointers and get a sense of what arguments get passed to them and maybe learn a little bit more on the invocations. I'm going to save you probably 4 hours of time here because none of them are actually really interesting. I don't think any of this code is invoked. Some of them seem to be doing some interesting registry interactions. So at first I thought I have elevated arbitrary registry read, but really this is the stage you'll be in. You're kicking rocks. Nothing is interesting. Going back to that command 7 though, I figured with some of the Frida tracing I was doing, I realized with some of these arguments that I'm passing along get interpreted in the function. The first argument is the path, which I control. The fourth argument is that 113 integer that I control. Now, one of the code paths here has a special condition for when argument 4 is sent as 114, something I initially missed in my analysis. In this code path, a new function, new variable gets reset to this hex 3000, which for the key node over here actually matches the SID for a high integrity process. So when you send 114 and the token gets prepared to run a new process, it actually asks it to do it in a higher integrity context. Really what it means is if I make my 113 114, it becomes elevated. So with my send command by name pipe, I just change that integer, increment it by 1, and now I have a child of ACC SVC, in this case Notepad, running a system. So an LPE as well. What's really cool with the previous work we've done is this works remotely as well. So you can get that elevated code execution if you want. Okay, so that's Acer Control Center. I don't have a reboot POC for you, but really it's another way to execute privileged code in a privileged context, but remotely. It's also pre-installed with some laptops, and while this is not a TCP service, the way they've configured this name pipe, like you intentionally have to code it this way so that it's available. Visual Studio has quite a lot of warnings when you do this, so that's an interesting one. Okay, the last target I want to talk about, and probably a little bit of a tougher one, was Razer Synapse 4. When you install the software, many of you probably have some Razer products. The GUI would look like this. I don't have any Razer products, so it shows me that I have nothing, but that doesn't hinder us from taking a closer look. I need to take a special moment and pause for the amount of processes that run when you have this stuff installed, just to change the RGB on your mouse. I'm a little unsure if this cost is worth it, regardless of what the software else does. Some of the key node for you probably already spotted the process. We're going to zoom in a little bit. This one called the Razer Elevation Service. As the name implies, it gives you a way to get elevated code execution. But what makes this target interesting is, unlike what we've looked at before, there are no listening ports, there's no name pipes, it's written in C++, so it's going to take me a little longer to figure out what's going on here, etc. One of the ways to get a sense of how this process works is when you attach procmon to a target. It gives you a nice way of what some of the Windows API calls, the ones that supports, how they function and when they would fire. More importantly, attaching procmon, I would interact with the GUI until at some stage there's some life in procmon, so that I can bind a feature in the GUI to what triggers a code path in the elevated context. This is really important. Once I realized that if I was to install more components, and that would trigger the code path in the elevated service, I sort of have an idea of what I needed to focus on. The client being written in Electron means all of the code in the sense of JavaScript is accessible to you. Node.js community supports a tool called Acer, which lets you extract the archive or the bundle of the Electron application to get access to the JavaScript source code so you can read how this works. And it's really handy. Depending on how the developers pack their software, it can be a tricky, minified mess, or in the case of Razer, it's actually quite easy to read. One of the things you'll learn when you start reversing this is you realize that they've implemented a foreign function interface which lets them call a native DLL from the JavaScript world. So for you to do Win32 API calls, they do the heavy lifting in the C++ world, just get the results back using this FFI. They seem to have maintained or are maintaining a private fork of this project over there, but really what this means is in the JavaScript world, with the same signature in which one of these functions are defined in the native world, you can make a call, and Node FFI will sort of deal with all the heavy lifting. It's actually pretty cool. It supports many architectures, many platforms like Windows and macOS, so it does a lot of hard work for you. The result being is the developer doesn't have to deal with the native world. They can just look at the JavaScript world and use it normally. Some of the definitions for how these things work when you look at the Razer Synapse GUI source code. For a very short moment here, I thought, are they using Frida to sort of interact with a remote service? If you've ever used Frida before, often you have function definitions that look like this. But really, these are just pre-computed definitions of what functions exist in the native world that they can call from the JavaScript world. As a last sanity check, if you look at the exports on this DLL called the simple service DLL, you'll see the functions match exactly what we've already seen in the JavaScript world, which is really handy. So for me to inspect how some of this stuff worked, I decided I'm just going to write some very simple C++ that also loads the simple service DLL, call those methods, and if I need to, use the JavaScript world to understand what some of the argument references might be. Should I pass integers, strings, what do they look like? In addition to, in which sequence should I be calling these things? In short, it's a bit of a more complex POC, but what you really get down to is this one function called simple launch user app process, which took 3 string arguments and a callback, a pointer to a callback. The tricky thing with these arguments, though, is they're not obvious in how they work. So I'll save you a bit of time, but to give you a sense of what you needed to pass along, you need to learn that parameter 1 is a folder relative to this app data path, specifically in this Razer App Engine user data apps. Parameter 2 is then relative to parameter 1. So you can't put a full path in there. You sort of need to know where this original path already exists. So if we wanted to run something from that context in our POC, we needed to pass an argument like common, which know that is relative to app data. It's something any user can write to here. And a payload, for example, add user.exe to run. Cool, and when I string all of that stuff together, compile it, it'll load the DLL and start executing the code from the exports that I'm calling. The DLL itself is actually quite verbose when you do a bunch of invocations. So one of the really nice things that it does is it tells you what's wrong. In this case, no surprise again, there's some PE signature validation that's happening. My add user POC is absolutely not signed by Razer, so as expected, they would deny it. We sort of progressed from our kicking rock state. I realized this is actually quite a hard one. I don't think I'm going to be able to get past this. Until I realized, but that signature verification just happens in that client DLL. It's not verifying in the elevated service, once it's talking there, that this PE is actually signed. So the way to get past this is to just patch the binary again, remove the signature validation entirely, and have simple service interact with the elevated service. So what does that get you? No error, which is confusing. New errors are good for progress, but when there's no errors, well, the POC didn't work, which isn't great. But you'll remember a trick we used earlier where we added the side-by-side assembly manifest to sort of ask it to run in a higher integrity context. Again, this is what it may look like. pwn.exe here is not signed yet, but when I run something like empty.exe with the manifest we saw before, we're now in a state where that process will try and run in an elevated context and will actually get right. So let's look at the demo for this local privilege escalation for Razer Synapse. The first thing that we're going to do is just double check that the service is running. This Razer elevation service is the one we're targeting. Next, what we'll do is we'll check the users, try and add a user, which we won't be allowed to do as we don't have the access to that. Finally, we'll run the POC, which should load the DLL that we've modified, obviously, to take out the code signing, interact with the elevated context, elevated service, and add our new user. This user is an administrator. Okay, so while we're preparing these slides, a colleague of mine goes, "This looks really hard. That's a lot going on. What's happening?" And he kind of made my LPE a one-liner. You see, the thing I haven't told you yet is the way to interact with that elevated service is actually a COM object. And I fat-fingered, we're sort of 5-6 days later into this thing, I'm not thinking clearly. I just absolutely went the wrong way in getting this POC to work. You see, using something like oleview.net, you can get the prog ID for what is this exposed COM object in the elevation service. Using some PowerShell, we can instantiate a new instance of that COM object, ask it which functions are available, and finally just call a function we want, which is in this case launch process no wait with a path, and the exact same thing occurs. Get rid of the DLL, don't do any of the hard stuff. This is much easier. So as a one-liner, my colleague shows me, you can just do this and the same thing will occur, which is really nice. Okay, so let's get to wrapping up a bit. I did have plenty of failed attempts. HP support assist, for example, you can see is clearly, I think a lot of people in this room has already looked at that. They've hardened that quite significantly. Gigabyte Control Center is really just a reminder of old school download managers. It has nothing interesting in it. I did have a look at Lenovo Vantage, but my energy was a little low at that point. However, Atreides Partners about 2-3 months ago released an excellent blog post looking at exactly the same target, but using some registry-based primitives to get code execution, which was fantastic. I highly recommend you look at that. As a little bit of a summary of what I've seen so far, there's this thing that I'm just going to call the Pwn triad when I look at the software. If there is a privileged service and you can identify some form of RPC mechanism, be it a named pipe, some arbitrary connection, arbitrary TCP connection or whatever. Check for broken auth, broken validation, because the chances are pretty good you're going to find a vulnerability. Here is a summary of the vulnerabilities and the CVEs that were assigned if you wanted to take a little look at this later. To take a quick segue on some of the disclosure stuff, there are some notes that I have here. The Acer's vulnerability disclosure was honestly frustrating. Their site where you report bugs has a WAF. I am going to report an exploit with a POC, and the WAF blocks that. Don't do this, or do something else. It took 2 or 3 days, but I eventually resorted to a GIST with a link, and their form accepted that. On the Acer's Hub vulnerabilities specifically, the DriverHub vulnerabilities, Acer seems to have strung along another researcher. The day I received the email telling me what the CVE assignments are, a little bit later, a friend in the community links me this blog post saying, hey, look at this cool bug my friend found. Now, 2 researchers obviously will talk to each other and sort of figure out what happened here. It turned out Mr. Brew reported the same vulnerability 2 months later. Instead of Aces going, hey, we're already dealing with this, it's fine, they sort of emailed the same email to him saying, here's the CVE with no credit or anything like that. So it was this really strange situation for them to create. That said, I think Mr. Brew didn't like it, so please go read his other blog post where he went for a whole bunch of other Aces stuff. I think is a bit of a retaliation. On the positive side, MSI responded amazingly. Their response times were really quick. They were the first with a fix, so that was a really pleasant experience in terms of getting some stuff fixed. And then as the very last one, Razer has a bug bounty program. Of course, I wanted to speak to the security team saying, hey, I want to speak about this publicly. But the difference between the bug bounty program and the actual Razer security team, getting to them was very hard. I got 1,000 emails of a loop of a ticket system on the inside with someone trying to figure out who knows what to do here. So if you have a bug bounty program, please have a way for researchers to get hold of you. It's kind of important. Okay, so one more thing specifically for RomHack. When looking at a lot of this software, I run into name pipes a lot. And I don't think the state of how we work with name pipes today is fantastic. Name pipes are everywhere. That's a tongue twister. And a lot of processes, of course, use this to interact with each other. Today, if you wanted to look at name pipes or how subsystems speak to each other, you have many options. One of them being Frida-based, which I honestly think is probably the pinnacle of how you would do this. Write a script, hook the functions, get a sense of what's happening, and if you need to manipulate something, you have everything you need right there to do that then. There are many implementations of this that exist already. There are some 2 examples over here, but all of them are based on this idea that there's a read file, write file, and variants that you hook to get a sense of what this comms might look like. There are many other non-Frida-based open source tools that would give you an idea of what pipes exist, what their privileges are. In fact, there are some of them that would bridge the comms to a burp instance so you can manipulate it and then send the comms back into the process. It's fairly crafty and quite handy. One of the other options you have, if you want to throw some money at the problem, IONinja's pipe monitor is just as amazing. It's got a really nice editor. You can also intercept, log, etc. So that's great. Or if you want to do it really cheap and nasty, you can write some PowerShell and sort of get a sense of what's going on. Anyways, currently, and sort of the last target I've looked at was Logitech's GHub. And what's interesting about Logitech GHub is it has 3 processes that runs, all 3 of which interact with each other using Windows name pipes. When I'm writing Frida scripts or using all of these tools, it sort of gets a little hard to keep context of what's going on. So I set out to see if I can build a different tool that will allow me to look at these kinds of targets easier. What I'm going to be releasing soon is a tool called PipeTap. PipeTap will allow you to attach to multiple processes at exactly the same time, leveraging a support DLL to do the hooking for you. You can do rudimentary things like listing pipes, enumerating their permissions, etc. But more importantly, it logs the comms that you can see, lets you export that, and interact with it in a way that's useful. You can do on-the-fly editing, so it kind of blocks the Windows API call. Here be dragons, depending on what the implementation is. But the reality is you can sort of get a better view in real time of what might be happening. Finally, and probably one of the most important features is some of these name pipe clients have, I don't know what the real term for this is, I'm just going to call it calling PID validation, where if a pipe client connects, you can expose who called, and they check if that binary is signed, has a valid signature. To get past that, if you inject a DLL in that target process and make the name pipe clients from there, you can interact with your target again. And pipe type will let you do exactly that. It's a normal named pipe client, but it's also a remote named pipe client. Once you've analyzed some of your protocols, you can also get to a point where maybe you need some more complex interactions, in which case pipe type also has a TCP to named pipe proxy. You can now, from anywhere, connect over TCP to a named pipe, potentially in process, and interact with it in ways that might be interesting to you. A quick screenshot of what that will look like is something like this. In this case, it's the proxy view. You've seen what burp looks like before. This is exactly the same idea with the traffic log at the bottom. Of course, this protocol is all bytes, so it's not a lot of nice ASCII printables, but it sort of gives you a sense of what it will be. For those here at RomHack today, find me around the conference floor. I'm happy to add you to the repo if you want to take an early play at it. This will go open source later in the year while we're still working on it, but if you're interested in this stuff today, let me know and I'm happy to add you there. Okay, so to wrap up, we still have products in 2025 doing silly RPC things. Please think twice if you need that bloatware, and if you can, do a quick triage of it, see if the pwn triad is applicable to you, and probably uninstall it after that. All of the POCs I showed you today you can find on the GitHub, so if you want to have a play or see some permutations, you're welcome to. That's what I wanted to show you today. Thank you so much for listening.
Right, thank you, Leon. Great presentation. So we have, yes, a few questions from the audience. I guess let's start with this one. Did you audit the patches and were they good?
Some of the disclosure processes were so painful that I sort of just accepted that the patch works. So no is the answer. Please. I am not so sure it works.
Okay, so task for our students.
Yes.
For the Asus thing, I guess the research, as the file name is kept and the file downloaded directly without a user prompt, did you check if you could traverse the path too?
That was actually one of the first things that I tried, and I kind of failed with the path traversal. What's interesting about it, where it downloads the files are other system-related, Asus DriverHub system-related stuff. So there's an INI file that defines which path takes which arguments, etc. So you can cause an arbitrary download to overwrite that file. I think there's still something there to play with. So no, the path traversal didn't work so well, but there are some other avenues I think is possible.
Okay, thank you. Next question. Have you, by any chance, tried to see if the CMD parameter of the reboot method can be manipulated with other commands? I believe this may be also related to the Asus.
So you control the command path entirely. For most of these things, you can say, what do you want to run? In my case, if I want to shut down, I can. If it hard codes what the function might be, in the case of, I think it was the MSI Center one, like the full shutdown command is hard coded. There's no manipulation that you can do there. But for the commands where you control the path, you can run anything. Yeah.
Okay, thank you. Last question. Did you get any problems getting a CVE number by the fact that you modified the binaries?
No, not at all, actually. The Razer interaction, I think they accepted the bug too quickly. Like, there was one of those, why aren't you fighting me? But my write-up was quite clear. These are client-side things. It's outside of the context for what the elevated service is. And honestly, kudos to them. At that point, I didn't understand the COM interaction yet. I think they did and sort of said, it's fine, we'll accept this one. But no, there was very little resistance to modification here. I think because it's clear where the security boundary is here, and that was really nice to work with.
Okay, thank you very much.